Okay, so we will get the show on the road here. So, a couple of things right before we start is to do two things. The tooling discussion that I said complete via video, that has to still be uploaded. I'll do that, so you'll have it complete. I already uploaded the file to the under files, but I've not done the video related to that. The other one is I have to finish up the second part, which is this last Thursday's thing on this is mold flow. Advisor. So this is where it takes the, so last class, if you recall, I went over the, getting into the module for the finite element analysis, right, the tooling, and then how to do a split mold tool, then how to do a standard tool with doing runoff surfaces, and then creating the male and the female from the part that way, and then adding the workpiece dimensions, and then basically providing the clearances with the flange and everything, and then producing the tool that way. So this was related to the third thing within that, which was the mold flow. So if you saw the hair dryer example, we had something like that. He had positioned a gate out here. I posted this video for you all to look at, but the gate position was here, and then based on that he wanted to evaluate the fill characteristics of this part, and from that couple of things stood out. If you saw the video, was how do you put the gate location. You can actually check for that before you actually run the check for if the gate, so basically it gives you like advice on is that an okay position to put the gate. From that you can of course look at the fill times, how much time it takes to fill, and the location of the fill, right, where it actually ends up filling and completing. Then you also saw the fact that it gives you a pressure distribution of the part. So that is the other thing that you would always be interested in. So that gives you a feel for what kind of injection molding tonnage you would have to go for to fill a given part, right? And then it also gives you the sprue and the runner details. So that also, if you look into that further, you can also put things like ejection pins. You can put the actual diameter of the pins, height of the pins, location of the pins. All of this can be already captured in the tool. So when you provide all this information, it builds you the tool base based on existing templates. You don't have to spend time building a separate tool base, right? The tool base is already part of the portfolio. It just picks up for a given cavity and then places the things according to that. So this video that I will post will have a lot more like I guess an example study and how to run a case study and things like that. So that way you should be able to run any part that you make. First, the general idea is run it through mold flow, make sure the part fills for a given polymer, which means you also need to give material inputs, right? Which means you saw that you had to select the polymer type, and then sometimes in this you have to generate what is called as the PVT curves. Anyone knows what that is? PVT stands for pressure, volume, temperature curves, right? So the dependency of pressure, volume, and temperature. So there are several ways of pushing the polymer. Is that just you essentially change the pressure and then get the material in faster. The other way is to increase the temperature, and that way you push the polymer in. The other way is to be able to adjust the volume of the fill and adjust the flow that way. But every polymer has a very specific PVT Typically P, V and T are plotted in a three-dimensional manner like that, and then for any given conditions you will have to monitor for different combinations of pressures, volume and temperature. You can generate a standard template for that polymer. So this is done through thermorheological characterization for the most part. So this is everything that goes into the mold flow advisor. You will also find the other thing it picks up is things like weld lines, and we have talked about weld lines before. Like if I change the gate from here to here, and here 2 gates, I start putting 2 gates, then the polymer will want to fill from both sides depending on same time, simultaneous or sequential injection, and then at somewhere in this locations you will end up getting these weld lines. And that weld lines, like I said, would be detrimental to the performance, and you have to worry about is that acceptable or not. And like in the cell phone example, you'll see that it has a bunch of, like I think I did this last time, you'll have a bunch of these holes, all the numbers where you press, all those become positions for weld lines when the polymer runs speed. We also saw that in parts where you have fewer of these points, you use what is called as knockoffs, right? You would basically not have a hole there, you would basically have a material that is not as thick as the rest of it but slightly thinner, so you can just punch it out after the flow is done. So that is referred to as knockoff, and I think we discussed that that decision has to be made based on what is the volume of the total part relative to that, does it make economical sense and so on. That would be the idea. So the subject of this video then would be to finish up on the mold flow advisor. So why am I saying all this thing? Because now all this thing will go into your two things. One is it will go into the remaining part of test 2, which is test 2B, and then the next step, which is the project. And I don't know if you saw my notes on the canvas, right? What I am thinking is we won't have a final as per se for the class, so I guess it's okay to clap, but finals is not there because we have enough work in place of the finals, right? So what we'll do instead is we'll treat the project as the extended work plus final all together. So that is one thing to note. Then the other question comes about is what is expected on the project. I started kind of giving you an idea what is expected already, but first let's spend a few minutes talking about the presentation of this exercise. So I want obviously everyone to present, and I just saw today, I did a reality check, we just have 6 classes left, either direct or virtual or what it is. If you look at it, I think December 5th is the last class day, right? Today is 14, so we have November 14th and 16th, and then 21st, right? 20th, that is, no, 21st, which is Tuesday, and then Thanksgiving, right? 23rd is Thanksgiving, which means it is 28th and 30th, and then December will have the 4th, that will be it. So I don't think we want to eat into class time for the presentations, and the absolute, then everything goes from there. The finals week starts I think on the 6th and goes all the way to the 14th if I'm not mistaken. So if it's okay with you all, what I'm thinking is to have maybe like either 1-2 hour sessions or full afternoon, whatever works for the class for the presentations in this time slot, in this time frame, 6 through 14. So you don't have to tell me now, but think through that, and that's when we'll have each person presents for 12 minutes, no more than 15 minutes per person, that's the thought. So if you do, I think 2.5 hour, 2 sessions, or an afternoon, something like that, we can plan it. Do you all know what is your most important final day in other classes? 14? So you have so something between 6 through 12 would work, right? Okay. So I'll send out a note on Canvas, just if it's conflicting, let me know, but that's the plan, more or less. So at the same time, you present as well as plus report. So all that will be due at one time. So that is very close to the end of the semester. I can post grades a day or so after that. Any questions or comments, concerns about this plan? Okay, great. No issues. It sounds like. Also, then, in terms of the actual project or product, whatever you want to call it, I have heard from some of you. Some have still not heard, right? So I need to know this week, please, by November 17th, deadline. If you already told me, don't worry about it. You will not. Please think about it and let me know. So that's the logistic part of it. Test Q was due today at the most, like final, either through WELD or in physical form, whatever works. Test 2A. Test 2B would be the FEA portion, and now I'll post that formally today, I guess. So today I'd like to take up this topic, which will be a separate topic. It won't mix up with anything we have discussed so far, but it's very much related to everything we have been saying, and that deals with eco-design, it deals with green, right, recycling, natural, bio, natural, whatever terminology you have come across, right, that's what would be important. So this is very much integrated in product design, because as you know today you can do, like I said, design for sustainability or design for impact, design for stiffness, design for strength, and so on and so forth. So in this, somewhere in the middle of all this, you should continuously be thinking about design for green or design for the environment. So this whole theme stands for design for environment. So there's a bigger aspect of this. It is not so much as to what is the near-term implications. You have to worry about what you leave behind for the generations to follow, right? So as an engineer or product designer, it's imperative that you have a social aspect to this and think, okay, well, the implications of what I'm doing today, how does it affect my future generation to come? Because that, if you just say, okay, I'll use all the energy I can, I'll do my best, use up everything, nobody needs to worry about it, and you are not conscious about the next generation. So that is one of the biggest cause. The other thing that's happening is a lot of it is tied to, of course, there's the social cause, like I said, and then a lot of it is happening because of the mandates. The mandate, when there's a regulation in place, then obviously everybody has to wake up whether they like it or not, right? You have to start trying to meet the mandates set forth in that case. So design products in this angle comes about from several motivations. So like I said earlier, fear is a good motivator. In this case, you're going to get penalized heavily. You're going to take all precautions to see that you won't get penalized, right? And that way, you can see the implications of this big time first being seen in the auto industry. So what's happening in the auto industry, anyone?
Cafe standards.
Exactly, cafe standards. So that is a huge impetus for this. And what is cafe standards, or what does cafe stand for? It's not coffee or anything, right?
I don't remember what it stands for, but you take your fleet.
Corporate auto fuel economy.
Okay. Yeah, so it's a fleet average fuel economy. So if like Ford has a gas guzzler, they have to balance it out by also offering some compacts with good efficiency.
That's correct, exactly. So all this, the CAFE stands for Corporate Average Fuel Economy. This is the mandate set forth by, from Washington, right, by Congress, saying that by a certain year, and I may be wrong on the year, but year 2025, they want all the vehicles to be able to give, at least within a certain grade, 39.9 say mpg, right? Or they may say that an economy vehicle may give standards of 54.4 mpg. So they rank it by class of vehicles, like for example the truck class is referred to as class 8 trucks. Class 8 trucks would be all the things like your Ford 150, 250, or the Silverado and that kind of trucks within that range. So those would be typically in the class 8 form as such. So these CAFE standards set forth that a vehicle has to provide that much of minimum MPG, miles per gallon, to meet a certain mandate, right? How do you, that is a certain mandate set forth by the Congress. The other thing is they impose very heavy landfill standards. So anyone knows what landfill is? So at the end of life, after you do all your garbage, put it in the trash, and the truck hauls it away. Usually they're taking it to a landfill. And they put layers and layers of landfill, and that's how they build up the mountains of landfill, right? And landfill costs are not, it's not free. Although it is going to a dump site, the cost of landfill now is increasing by certain amount of thickness of the landfill or X amount of tonnage that you are putting out there. So that landfill costs are going to be very high. So all the auto manufacturers are also now mandating that the vehicle should have significant end of life plan. So in Japan and in Europe, this is even more stringent than the US. They already have like 95% and above goals for end of life recycling. So if BMW makes a car or Mercedes makes a car, they say that the manufacturer has liability of at least 90 to 95% recycling of everything in that vehicle. So they just cannot use materials which cannot be friendly for recycling. They cannot use things which are compound plastics which may have problem in recycling, right? So therefore there must be a plan, and they're saying, okay, if you don't have that, then you must be able to cover the cost of landfilling that, or find a way to close the loop or other uses of this in other areas so that it doesn't become the liability of customer. It has to go back to the manufacturer. So these mandates, like I said, in Europe there is certain standards, Japan certainly there are standards. So where there is the population density is high and space is limited, the mandates are even more stringent. Of course in the US still the land is still substantially large compared to the population density. So you're talking about less regulations, but they are coming. I mean, if you're talking 95% here, still this between 80 to 85% in the US manufacturing. So if Volkswagen makes a vehicle in the US for US consumption, it would have a certain different standard than if the same vehicle was made by VW in the European plant used in Europe. So these standards have to meet that kind of requirement. So all of these again goes back to the need for mandate, otherwise there would not be that compelling way to go for any green. Like you know that today cost of gas is what, $2.40, or it went from $1.99 or something down to $2.40 in that range. There was a time gas went up to $4.50, coming close to $5 just a few years back. When the price of gas goes like that, then there's immediate attention to alternate energy. Everybody wants to look at solar, wind, thermal, other areas. But then once the price starts dropping, again the alternate energy focus shifts. It comes back to fossil fuels, right? Oil and standard ways of using energy and so on. So that also is a big driver for. Can you adopt green? Are there going to be any cost benefits of adopting green? So sometimes it's mandated upon you, sometimes it's a natural thing. Sometimes a full society adopts it as a habit, like obviously in the Netherlands or in Scandinavia and countries like that, you can't get into a hotel and just turn the lights on until you put the key in the slot. Only then the lights would come on. If you try to flush the toilet, you have like a small setting for water, a large setting for water. So every aspect is so carefully controlled from an environmental friendly standpoint. It's a habit of the society that is, even every single house in Germany, if you go to drive through rural areas, half of the homes have solar on top, right? And there's not even that much sunshine there, but still it's a habit that is mandated by the society. So some of this has to be trained, some of it is forced upon you, but the whole goal, things are getting green, as said. And you know, like the Owens Corning logo, pink is green, right? When they have all this insulation material in your homes and all that, that's pink foam. That's meant to add to the insulation value of the home. So that's their logo. It's pink for a reason. It is branded as a pink insulation. But the whole goal is pink is green is their logo, meaning every insulation you add, it's going to add to the green ranking for your house. So that's the context of this discussion that we are trying to have. So I have to, I guess, look at it in 2 or 3 ways. So when you look at green, green would be in the form of literally bio, right? So if you look at it, and I'm going to use a car as an example because it's as good as any, right? So if you look at a vehicle today and everything in the inner body, like if you look at underbody, upholstery, you know, the carpeting, the things in your wheelhouse, wheel well housing, all these things, is upholstery I already said. If you notice, all these things now are using a lot of natural fibers in their makeup. Natural fibers means what fibers? The reason it's called natural fibers is because it means it is from organic or natural materials. So these are for plants, these are from trees, shrubs, and so on. And I'll show you some slides about the actual way to classify these. But natural fibers is a way of life now in the vehicles because that's one way you can pretty much be assured you're using the least amount of energy in producing those, and the fact that at the end of life you can biodegrade those or you can dispose them in an environmentally benign fashion as well. So all of these things, before you do, we should be familiar with the term called embodied energy. And anyone knows what that means? Except that Komal is working on it in our group, but what is embodied energy?
Energy from raw material to finished product.
Exactly. The real definition is embodied energy is the energy required to produce one kg of anything. This is in the raw material form of the definition. So if I require, let's say 57 megajoules per kg to produce acrylic as a plastic, then that is the embodied energy in producing the plastic. Yes, sir?
So how is that average for like mass production versus small production?
Yeah, so it is in the, even for small production, if this per kg is going to cost you this much to make that material, it is still, whether it's you're making 2 kgs of it or you're making 100 kgs of it, right? It's within the same definition. What you are referring to is basically volume-based scaling, right? So this we are talking about absolute cost of producing 1 kg of the material regardless. So we are not scaling it yet in any fashion in terms of a volume-based production. But certainly that's a very good point. In the same context, if you look at energy to produce, let's say, a kenaf or a jute fiber, I'm just using a natural fiber as an example, you can see the energy to produce that is no more than 8 to 9 megajoules per kg. Okay, I'm just talking about a reinforcement fiber as an example in this case. Now in the same context, if you try to produce glass fiber, say, and I may be off on these values, but please take it in context of comparison, it's like 35 megajoules per kg. If I look at going for carbon fiber now, carbon fiber is going to be very energy intensive process. It's upwards of 130 megajoules per kg, right? So the cost of producing that material in that quantity, right, is going to be very much had to be captured in the pricing of that material, the products that come out of it, because all these energy costs at the end of the day is being passed on to the customer, right? You're passing this on to the customer then. You're making your profits, etc. along the way. But from a standpoint of green, the goal is to try to minimize this as best as possible. And that's achieved through process integrations, process innovations, heat losses, finding ways to contain them, finding insulation, all ways in which that energy cost could be reduced. Like in carbon fiber, just 5 years ago, this may have been 3 times this cost, but by becoming process efficient, it starts becoming less and less over time, for example. And you see these examples in your home as well. If you're buying a new home, usually you will ask for an inspection, and if the inspector is a more sophisticated firm or company, he will bring his infrared camera along, and then they will point the camera to different parts of the house to see which windows or which openings or which locations are resulting in loss, thermal losses. And that could be from years of usage. They would have to come back and fix, or they know they have to add a insulation around these areas. So that way your home then eventually becomes very energy efficient. Then of course you have seen energy efficient double pane windows or doors. All these are means of reducing the overall energy consumption even in day-to-day life. Or they put a geothermal pump, for example. So those are additional ways of addressing that issue. So this term, like the other definition of embodied energy, is like Jared said, is the energy to produce something from material to product, raw material to product. And this is where some of the scaling may appear from this question about how does it change with volume. Here if you produce 10 parts versus 100,000 parts, so you're using a certain amount of equipment time, a certain amount of energy consumption, you're getting discount for a certain volume of energy usage. All that gets into accounted for in this calculation. But embodied energy is a term which is not an absolute definition. It is defined in a number of ways in the scheme of these things. And Granta, of course, has or the CES has a way to account for this. If you're doing energy versus some calculation, you can actually plot those, just like you can plot modulus or strength or so on. So this doesn't become a nebulous thing. You actually have a quantitative way of accounting for it. So just look at a few slides then. So this is one thing I picked up from the charts here, right? So this is a chart of embodied energy against different classes of materials, like metals, polymers, ceramics, and hybrids. So this chart is shown more as a, in this, not a bar chart, but plotted in this manner. So in the category of metals, you see he goes from titanium alloys all the way to cast iron, and then here you see that like these high-end alloys like titanium, magnesium, vanadium, tungsten, aluminum, right? These have much high embodied energy compared to cast metals or carbon or low alloy steels. So obviously you see that there is a lot of bulk consumption in the steel family right here for the reasons that the cost is proportional to the energy within that class, right? So where applicable, these materials are the materials preferred. Only when you have high-end applications, you can be justified in using the higher embodied energy alloys in metals. If you look at composites, these are mostly thermoplastics, but PEEK is like the Rolls-Royce of thermoplastics, right? Polyether ether ketone. Price of PEEK is about $1.80 to $1.90 a pound. Even on a lower end side, it could be upwards of $100 versus PVC, PE, PP, and so on. These are commodity plastics, like less than $1 a pound to $2 a pound. So you have a price difference of almost a magnitude higher from going from here to there. And some of the reasons are in the embodied energy to produce those polymers, right? That's where the answer is. If you look at ceramics, concrete is of course the cheapest material. Wherever possible, you are using concrete, plaster, brick. But if you go for things like aluminum nitride and boron carbide, these are highly densified ceramics, which are very superior in properties, but then you're paying for it because of the energy to produce those. Metal foams, like these are hybrids, we'll talk about this in another class. You can see that bamboo, for example, this is the class we are talking about, soft and hardwoods have much lower embodied energy, but as you go up to complex foams like metal foams or sheet molding compounds, composites, the energy consumption goes up. So this, like I said, has very quantified way of calculating this, and I would of course post this information here. This is on a per unit volume basis. I don't think much will change in the structure, but there are different ways of representing this, but the idea is what I wanted to convey from this chart. So this is one way you can see that CES does take this into account. The other, so we said we are talking about natural fibers. Maybe a little bit all over the place, but and some of you who took my class last semester have seen these slides, so I apologize for the duplication. So if you look at classification of vegetable fibers, like they call it, right? This is just a partial listing. If you look at vegetable fibers, you could think of using the stem for something, the leaf for something, the fruit for something. But all of these are actually being used in products, right, today. How? Like if you look at stem-based fibers, banana and flax would be examples of that. That's where the maximum reinforcement fibers can be derived. Leaf fibers in the sense of sisal and pineapple give you high-strength leaf fibers. In the fruit fibers, of course, coir or cotton give you the same advantages as such. And this is only, like I said, a partial list, but any plant, there are useful portions of the plant which actually you could derive and use it in structural or semi-structural or other applications which are useful for value-added products actually. Sometimes you could take a synthetic material and replace part of it with a natural material. So at least you'll have a certain portion that is being used from a natural material. And the way you get credits for using natural fibers or natural materials is even if you have a partial content in your product, the mandates are such that you get full credit for a green product that is useful. So you don't have to have 100% green, because sometimes you can't get the performance by going to 100% green, but you may get good amount of performance by going, say, 40%, 50%, a certain fraction thereof. So that's one mindset. In fact, automotive very rarely uses 100% green. We'll talk about why that is the case anyway. I'll come back to this. But here in these slides, I'm calling out every single fiber that's out there, like here, and giving you properties, strength, stiffness, toughness, strain to failure, everything that you need for your decision making. So you see, I listed only few there, but if you look at all the fibers out here from sisal and hemp and quinoa, flax, banana, oil palm, karua, jute, coir, pineapple, right, all on this side. And then sugarcane bars, rami, jute, pineapple, again, it appears on both sides for some reason, cotton, waka, date, and bamboo. Not all these plants are available in a geographical region. You can see some are very much in Asia, some are in South America, some are in North America. So if your product is going to be based on the choice of these fibers, you also need to know what your supply chain looks like, right? Like if you say Ford is using Ford uses a lot of soy in their soy is not listed here, but they do. They use a lot of soy in their seats, and they do foam seats, which you sitting all your passenger seats, driver seats. They have essentially a lot of soy mixed, blended in with synthetic polyurethane as well. So in that particular case, you have to see, is there that plant availability in the particular region. Like if Ford is producing foam seats in Mexico, they don't want to transport the entire thing from, say, Europe to Mexico, right? So they have to be able to get the source is close to the production site. Because the transport costs add to the whole production cost significantly. So the other factor is if there is a famine, or if there's a water shortage, if there are other issues, natural calamities, freezing, as you know in Florida, oranges go completely out of whack season because of a certain freezing rain. So that leads to uncertainty in the supply chain for natural materials. Then the manufacturer cannot be waiting for the next crop to show up. They have to have plan B. So always when they use natural fibers, they also have synthetic solutions in blends to account for that uncertainty in the supply chain. The other thing that happens in this is the plant-to-plant variation, right? If you took a stem of banana and cut it across, you're not going to have the same cell size through the entire plant structure. Even in the same field, you're going to get a wide variety of variables because it's a natural plant. So that averaging has to be done through blending of synthetic in there. So all these are some issues when it comes to using natural materials in your use, right? So I'm just giving you in the next few slides, and I'm not going to talk through because you're as you can read it as well as I can. But I've identified each tree or each plant. I've shown you which portions of that would be useful in a product, and then typically what would be their composition in terms of cellulose, lignin, hemicellulose, that is the composition of the product itself, and then what kind of properties you can expect in terms of strength, modulus, that is strain to failure, and toughness, right? So if you're designing for impact, you want to probably consider a plant which may be in the high range of the toughness value, for example. So there is a lot of design usage from this type of information. So that's what this particular slides are about. Any questions about this or comments?
Do you have to worry more about the decay with the natural, decaying best with the natural materials rather than the synthetics? Does that come into play?
So that's a great question, and he's not even formally taking the class, right? So that's what no, thanks for that. So basically, yeah, it is true. What happens is, that's a factor I forgot to mention. Natural fibers are prone to mold. They're prone to biological attack and ants and other things that termite and so on. So certainly, when it's used in a product, there's a lot of preparation in terms of interfacial treatment that is done through. There's stages of either sodium hydroxide treatment or thermoplastic resin treatments in the fibers to block off any access to moisture. The other thing with natural fibers is that they are moisture sensitive, right? They can swell. So if you design a part which has to have a certain dimensional tolerance, they make it a synthetic material versus natural, you can expect to see that the part will go out of tolerance simply from the swelling effect from that. So that has to be curtailed by proper treatment of those fibers. So there are pre-steps involved before actually just using them directly in a blend or application, for sure.
Another comment for that, for degradation, you also have to worry about processing temperatures.
Correct.
So if you're using it like compounded in for injection molding, you really have to pay attention to how hot you're taking the resin because it can start to degrade the fibers.
Absolutely. Again, another great point. Yeah, these are sensitive to temperature. At some point, they will start discoloring or blackening, or that's again certainly a process consideration. The smell is the other thing because you can do everything, but in the natural fiber, odor can be a disappointing odor. Sometimes the customer, it won't have a new car smell, but it will have like a old tree smell, and sometimes people don't like that, right? It's hard to get rid of that. So you need chemical suppressant to completely eliminate or suppress the odor. So a lot of chemistry goes into natural fiber before it's put into use directly. Okay. Sorry, I'm going through 2-3 different things.
In the previous slide, there was something eat, break. What was that?
Say that again, Mohammed?
In the previous slide,
Yeah.
there was something called eat, break.
Oh, not eat, that's epsilon, man. That is
Epsilon.
strain at failure.
Okay.
Epsilon sounds like an E. You must be hungry. It's epsilon, right, at break. So that means it's just elongation. You're right, it looks like eat, right? Elongation. It is the strain to failure. Yeah. With this thing, eat and break. Two very important words. Okay. So this is what I was saying, that the urbanization of all cities, right? Global climate change and growing petroleum consumption, all of these are drivers. This is an interesting statistics. If you look at the US, of course, US has historically had, what, 2 cars per family or 4, depending on that. But China today is with 13 vehicles per 1,000 people. That's where US was in 1930, right? So what's happening now is, in all these countries, like the US historic is captured by the red line here, and then all the other growing countries like industrialized Pacific, Western Europe have similar volumes of vehicles coming up, right? But all this bottom side, like if you look at China, Africa, Latin America, former Soviet Union, Middle East, I mean, in terms of that green bar, they're going to start moving up to the top as well because of the explosion of vehicles in this side. Like India, where I grew up, you can, many of you here can see from your own experience. Of course, you are a new generation, but when I was growing up, we had, car used to be a luxury for a family, right? Today, if you go back, most of the homes have cars. It's no longer it's almost a necessary or need. So all the middle class now has the affordability of buying vehicles. So in that kind of infrastructure, this is going to continue to grow like crazy. So that's the moral of this story here. If you look at the production and the consumption, these are areas in which oil is produced today and consumed, like cars, light trucks, air. If you add up all of these, actually, in terms of cars, you're talking about 4 million barrels per day, right? If you look at air fuel, it's about 16 million barrels per day. Again, all these curves are essentially growing, no matter how you look at it. And sometimes you may have dips based on economic conditions, but so these are all the drivers for why green is becoming that much important. These are some historical things I'd like you to review, how the cafe standards have evolved. What used to be started with, actually the first cafe standards were set forth in the 1970s as what is called as Clean Air Acts like that. And then eventually it transitioned into what is now today known as cafe. Then this PNGV was another initiative put forth by the Department of Energy in this late 90s. Then President Bush with the Freedom Car and so on, right? He pushed the agenda further from 2002. Then DOE came up with the 21st Century CD, the 21CD initiative for trucks. Then Bush rejected the Kyoto Treaty for that, and then basically he said that we'll put that much more into R&D effort for clean fuels, right? And then now this 2003 Freedom Car expanded into what is called as the Hydrogen Fuel Initiative. So I guess I'm telling you all this because as you all get into your professional careers soon, you are going to be hit by some mandates which then you have to start reacting to quickly. And therefore, it's good that you are aware of the transitions, how they are happening. So this slide said during the Obama administration still, but there are a lot of impact. So he said that in 2016, so the figures I wrote were even further down, right? That this has to be already met, 35 to 39 miles per hour gallon for cars and 30 mpg for light trucks and SUVs. So that is already a mandate, right? So when you do that, they have a big life cycle impact of reducing 1.8 billion barrels of life over the over billion barrels, right, over the life of the new passenger vehicle sold in the 2016 period. We are already at 2017, so these slides are definitely old, right? So just to put this into perspective, 1.8 billion barrels is more oil than US imported in 2008 from Saudi, Venezuela, Libya, Nigeria combined. So that is a very broad-reaching impact when they come about with these standards. So that is what I want you to appreciate more or less. Also in this case, the mindset of the consumer has changed. Like if you look at in 1950s, every year they wanted an annual model change. They didn't care about size and fuel consumption at all in the 50s. There was no such requirement. But later in the 60s, they wanted more safety on vehicles, so they started adding more of those features, right? Then in the 70s, you had the oil embargo, so you had the oil shock that hit. Then came automation in the vehicles, right? And then today, you're saying that 50 to 100,000 is generally considered a high volume. But after that, you need to again change the design for consumer acceptance quickly. So in up to 50s, you could produce up to 300,000 units for any model. It was a very stable consumer base because the model choices were limited. Today, because of the number of options, the consumer wants to see so much variety that even you see that 300,000 has dropped to like 100,000 cars would be very high volume producing cars in this case. Like Toyota makes about 250,000, right? Is typically there, like a Camry, for example. It would be very high volume. So it's well known also that if you reduce 10% of the weight of the vehicle, you can get 6 to 8% fuel savings of the vehicle. So that is a big driver there. If you can learn to take off weight and also take it out with the help of natural materials, then you're actually going to keep adding to that goal of saving fuel simply by weight savings. The other option, of course, is you are changing the powertrains. Today you're doing fuel cell, right, hybrids and other powertrains. That's another way to get to fuel efficiency, but by doing this you're actually adding more weight to the vehicle because you have to accommodate more hardware, more of the... So powertrain changes are other ways of meeting CAFE standards, but then you are paying in terms of added weight. So this is again why we are talking about this. I'm just giving you, don't need to give about the challenges in this work. I'm focusing more on the natural material side of things. So let's go to the natural fiber discussion because that's what we're talking about. Okay. don't know if you see it. So how do you design then with these natural fibers is the question, right? Like I said, these are some of the fibers in today's vehicles, like kenaf or jute or flax or hemp. You will not again notice these because they are buried with the carpets and upholsteries and everything like that. But like I said, from the variation or the differences you get from one fiber type to the other, you have to somehow equalize these properties, right? And that is done by, like I said, blending it with different fibers. So this is a kenaf plantation. The kenaf fiber, you can see, provides you very long fibers, which means that it gives you very good strength in the resulting composite. So typically fibers which give you high aspect ratios are preferred in case of these studies. So that is one of the goals when you're doing design, to select those fibers. So if you look at today's fleeces, like these mats are what is typically used to produce your headliners. If you look on the top of the vehicle, there is a soft touch headliner. That's from these kind of fleeces. So these fleeces have a blend of natural fibers with polypropylene fibers. They kind of mix them and compress them into such mats. And these mats generally have very high loft, so you can apply compression and change the aerial density of these mats to different thicknesses. You can make them very dense, or if you keep it slightly open, you have a lot of air entrapped in there, and that makes it very good for acoustical insulation. So today's car, if they're so quiet, right? Even if the engine is running, sometimes you may not even notice it's running, or the radio is playing with a very crisp sound because of the acoustical quality of the interior. And a lot of these mats are meant for acoustical functions as well as shapeability. They are produced in rolls, flat rolls of 48-50 inch wide, but then they can be thermoformed to shapes to give you that contour on the inside. So that is done by changing their mix from just natural to synthetic fibers. Usually they have, in this business you measure this with GSM, how many grams per meter squared. It's basically, in this case, you have 300 to 2000 GSM. 300 GSM feels like a felt cardboard. 2000 GSM feels like a very dense, like the consistency of a computer cover, for example. So you can see how the mat feels to touch in terms of its aerial density, just by different degrees of compaction. You can also see the advantage of natural fibers. You can have very deep draws without tearing. You can't do this with standard materials. Like in natural materials, the fiber has, so to Mohammed's point about what EAT meant, you can see this is where it stands. You can actually have very high elongations before it tears, right? So you can draw deep trays. In vehicles, you have a lot of this type of componentry, right, where the material has to get drawn into shapes. And that's done very effectively with such fleece materials that we can produce. There's a lot of tendency to use sandwich materials in this, where the core could be natural, the skins could be natural, or one of the two could be natural. It all changes. Like the Navy uses this in a big way by using balsa wood core in this case. Like in Navy, what they do, all your ship decking and all that is using balsa wood, because balsa has cells which are naturally shaped to run in this pattern, correct? Like if you look at the cell geometry, it has a hexagonal shape which goes down in this direction like that. And being that it has very high resistance to what? To bending, right? It basically has very high flex rigidity. So in this particular case, this is all natural, the core. The skins can also be made from natural materials, or you could use synthetic glass, just keeping the core as natural. So you don't have to use all natural if that hurts the application as well. So that is something to keep in mind. Like I think I showed you how the sandwich effect works, right? And you all have done this, like top goes into tension, bottom goes into compression, right? So Other places where you can have this is in areas of having a need to bond or clip. So here you have a sandwich material in a upholstered form in a vehicle, for example, where you have a bonding clip that is attached to the base, and then the whole structure has like a soft touch textured feel, which is very common in automotive parts. You have like a leathery textured feel on the skin. But then below that, you have like a natural fiber fleece-based mat, which is acting as the core. So this is used for design, weight-efficient designs. So this is like all the list of parts in the automotive. If you go from glove box, door panels, trunk floors, and then see what kind of fibers are actually used in that, you'll find that, like, I think I may have it featured in the Mercedes Benz. I told this in the last class as well. You have about 50 parts produced with natural fibers, either in the blended form or in with synthetic form materials. Acoustical quality, I was trying to say this earlier. This is a comparison of a fully consolidated polypropylene glass fiber panel, and the y-axis here is the acoustical absorption, how much sound gets absorbed. Obviously, if you look at a fully dense consolidated panel, it doesn't really absorb much sound, right? Most of it is transmitted through. But if one way to do then is to allow the glass to slightly loft and not go to full consolidation, and you can see that that does bring up the acoustical insulation greatly. But then the natural fiber here, which is the NF, which is the black curve, has very good qualities, comparing that to synthetic materials as well. So it can be used in acoustical applications as an alternate to synthetic materials. And usually acoustical absorption, you see, it's very difficult at low frequencies as opposed to high frequencies.
Do you ever grade those, like the PPNF and the PPGF, so that you get the lower end frequencies as well as the higher end frequencies to be absorbed?
To say that again, do you ever?
So do you ever combine the two? Say you have one green curve there and one blue curve. Do you ever put those materials in the same sandwich panel so that you absorb an entire range of frequencies rather than just a higher range?
Yeah, no, that's a good point. So actually these, although it says polypropylene natural fibers, there is some blend of glass in this regardless, right? So in both of these cases, these are very similar panels, if you will. So, but in general terms, arresting low frequencies is very tough in an application, no matter, unless you increase the thickness to a very different level. Then it's one way to absorb low frequency, right? Like I give an example in like the NDA class we talked. You sit in the room and there's thunder happening outside. You can still hear the thunder no matter how well the walls are, because it's a low frequency sound. It can enter through the medium, right? If you have high frequency, like a vehicle going through a bump or something, you don't see it inside because the high frequency vibrations dampen out very quickly. So that is it's a challenge of just the geometry of getting that wavelength to be contained in the separating wall. So that same issue is seen in this case. You will hear rumbling, and even low tire rumbling comes through the vehicle sometimes, right? That's because it's a low frequency sound. You will hear it through the That's why you had a lot of constraint layer damping, like they say, shear layers to absorb that through shearing of two materials. That's one. A lot of damping is added on the underbody to, if not the road noise can be very annoying because it's low frequency. So yeah, this is the picture I was looking for. So you can see every single part of this vehicle is, all these are the separated parts in natural fibers. And they're all, you will not see a single part because they're buried in your interior componentry. They're always covered with carpets or upholstery and things like that. These are very nice examples. I think this is I think it's a Daimler Chrysler vehicle. It's a pressed panel for a door inner. Again, this would be the inside of your door. Again, it's covered with the upholstery. You will not see this, right, because it's right behind that door. But the thing to note here from processing standpoint, you can start a fleece. You can take that fleece into this shape. You can do all your post operations like drilling, cutouts, etc. Just like you can work with glass or carbon fiber panels. So the processes are very scalable across media. And this is a blend of 50% Kenner, 50% polypropylene, 1600 GSM, because it's a door inner, it has to be highly impact resistant. It's a high LU density. These are more examples from other components like parcel shelves. This is seen a lot in SUVs, right? Load floors as well, when you're dropping the floor and pulling it back. That's all. These are natural fiber inserts. These are actual VW Touareg, the Porsche, Cayenne, big trucks. I think this truck is a truck in Europe. It's not an American vehicle, but the full front and grille is a natural fiber. Door inserts. The other fiber that's making it big in the natural world is basalt, and some of you work with this. Basalt fiber looks just like carbon fiber, but basalt is produced from lava rock. So as you know, lava flows, molten lava flows. So if you think of that molten lava flowing through small orifices and then drawn into fibers, that's what basalt fiber is. So the beauty is, it is a natural lava rock fiber, so it can take up to 2000 degrees C, no problem, very high temperature resistant. And also the fact that it can be very flexible, so it can be woven into shapes and fabrics. It can be drawn into filaments. And then, so it looks just like carbon. Its density is similar to glass, and its modulus is about 70 GPa, close to glass modulus. So it has all the attributes of glass fiber. It has the looks and feel of a carbon fiber. So it is like looked upon heavily in many of, even our own projects, we are looking at basalt in this case. It has a grayish black appearance, not like a pure carbon black. So that's a shiny, silvery, blackish appearance. And in terms of cafe, I want to mention this is wonderful because it, when you do an end-of-life incineration of the part, say you burn it up, the basalt fibers will burn your incinerator very clean because it is a natural rock-like material. It cleans the inner walls of the incinerator as opposed to using glass fiber, which will choke the incinerator. So as you start, it's like cholesterol, right? It chokes your engine stand. So glass fiber after a while will give you a heart attack, right? And in case of the basalt fiber, it's like a stent. It keeps cleaning as it goes through. So that's the advantage from a green or recycling point. You're going to really consume less energy in the end-of-life disposal.
How does the embodied energy compare between basalt and glass? Because you could also argue that glass is natural.
Yeah, sure.
From sand.
Yeah. But some of the additives that go into glass fiber make it behave that way, certainly.
Okay.
On a unit basis, Alex, I don't know. I have to check that.
Probably the difference in the minerals between the two fibers, right?
Right.
Because one's like
Well, it's just
silica and
I would guess that most of it is like processing temperatures where most of your embodied energy is going to come from. So like how high do they have to heat up the basalt to turn it into fiber?
Yeah, that's a good question. I know glass is in the 50s, 50 to 60 megajoules. Basalt, I don't know. To be
Okay.
honest.
I don't know, we laser cut it recently, so I can't be that high.
Yeah. I mean, it's,
No,
I would,
that's indication.
I think it may be in the same ballpark as a ceramic fiber, but
Okay.
I don't know the answer to that.
I mean, it's controlled coating, right?
Right. So these are some compound comparisons, I guess. Again, silica and all the additives that go into glass. So you have borosilicate glass, or you have other glass varieties. All that is based on what compositions you add in the glass. But you see, silica content also is very similar. The alumina content is also very similar. Some of the other content, the calcium oxide is slightly less. MgO is, you can argue, is within. So there's a lot of compositional similarities, but the very nature of the material is where the differences are. And then basalt compared to other fibers, you can see very decent values of strength, almost comparable to glass. Similarly, modulus, like I said, is about, actually basalt is higher than glass. I was imagining it's 70. Elongation of break, which is very comparable, 4% is very decent elongation. As you know, carbon is less than 1%, right? It's very brittle, but glass and For impact applications, it's comparable to glass. Density is very similar, 2.5 in that range. Max service temperature, melting temperature of 1450. So I may have exaggerated the thermal characteristics. And now one area it's used is in the headliner of the Honda, I think it's the Acura model if I'm not mistaken. So this is a product by Asdel, which is now Hanwha has acquired Asdel. So they call it Volcolite because coming from volcano light, that's their branding. And the headliner of this is a basalt headliner. Again, their motivation is to demonstrate end-of-life friendly incineration for this application. Again, the sound absorption is excellent. It is felt like in this case. And then this is what I said in terms of incineration. Sorry, I may have to
How common is it to use incineration for end-of-life for automotive parts?
That's a good question. So when you're dealing with complex plastics, sometimes there is no economical way of separation of them. Then you go for pyrolysis or incineration as your option, because then if you can get the particles to a decent aspect ratio, they are still applicable in admixture and additives in other materials and so on. But it would be a last resort, but sometimes that is the more economical one than trying to separate the fibers or trying to chemically dissolve. That can be more energy intensive, right? So I'm going to stop here for today. I just I'm sorry, I'm running through the JEC to this visits back and forth, but anyway, we're out of time. I'll continue this on Thursday, and we'll so shape, hybrids, finishing up this, and sandwich. So I have at least 4 more topics to cover, and cost. Let's not forget cost. 1 class on cost, 1 on shape, 1 on hybrid, and 1 on sandwich. That way we'll be in the, and then I'll put the videos for the tooling and for the mold flow, and I believe we should be caught up. I've also posted a bunch of stuff. Don't see the files that I've added. I think everything on there should be current as of today. If I'm missing something, please advise me and I'll post it actually. I may have missed.